Simple multiple linear regression, ANOVA and COVA are all examples of linear models. In each of these cases, our primary need is to estimate the parameters that are involved in these different methodologies, so that we can use the estimated parameters in the model and use these models for future prediction. Now, sometimes what happens is the data that we have at hand does not always meet the assumptions of linear model. Under such circumstances, we can no longer use the usual method of estimating the parameters. The usual method which is most commonly used is the ordinary least square method. Now, in cases where the assumptions of linear model are not met with, we have to resort to other methods, one of which is the generalized least square method of estimating parameters. In this module, we will learn how to compare the estimates that we get from ordinary least square and generalized least square, and in the process we will also learn the theoretical properties of both the methods. In this module, we wish to look at a comparison of the ordinary least square and the generalized least square method of estimation of parameters in a linear model setup. The simple linear model is written as y equals x beta plus epsilon, where y is the vector of dependent variable or response, x is the collection of the explanatory variables, or x is a matrix where the columns of x are the explanatory variables, and beta is the parameter vector, epsilon here is the vector of errors. When we learnt linear model, we have also learnt about the assumptions that are underlying in a linear regression model. These key assumptions are as follows. Linear relationship, this is the first and very important and basic assumption of linear model. The relationship between the response variable and the explanatory variables have to be linear. Second assumption is that of multivariate normality. We assume that the error terms involved in the regression model are normally distributed with mean 0 and a constant variance. We also assume a third property of the linear model, which is no multicollinearity. Multicollinearity means there is correlation between the explanatory variable. Now, under the linear model assumption, it is expected that the explanatory variables are uncorrelated. If the variables are correlated, it is said to have multicollinearity, and we have to resort to different methods to take care of the problem. We also assume that there is no autocorrelation in the error terms. What this means is that the successive error terms are uncorrelated. And the final assumption is that of homoscedasticity, or the assumption that the variance of error terms is assumed to be constant. It is this assumption which is, when violated, we say there is heteroscedasticity present. Now, in the least square technique is probably the most popular technique of obtaining the estimates of the parameters in a linear model setup. In the least square method, we estimate the unknown parameters in linear regression model with the goal of minimizing the sum of squared differences between the observed response and the response predicted by linear equation. There are several reasons contributing to the use of this technique. There are several reasons why this method has become very popular over the years. They are: the most common estimators can be casted within the least square framework, and this is why the use of ordinary least square has been very popular among statisticians. Using squares makes the least square method mathematically very tractable, and this is one of the other reasons why the use of ordinary least square is very popular. Also, a third pro of using least square is that the mathematical tools and algorithms involved in least square method, such as derivatives, eigenvalue decomposition, singular value decomposition and such, have been very well studied for a relatively long time, and the properties of these tools and algorithms have been studied so extensively that their use has been very popular among statisticians, making least square the most favorite method of obtaining the estimates of the parameters. The least square method is widely used to find the estimate of the numerical values of parameter to fit a function of set of data and to characterize the statistical properties of the estimates. The properties are such as consistency and asymptotic normality. The simple version of the least square method is the ordinary least square method, or better known as the OLS method. Most commonly used OLS is when all the assumptions of linear regression are met. A more sophisticated version of the least square method is the generalized least square method, which is typically used to estimate unknown parameters in linear regression setup when there is heteroscedasticity in the dataset or a certain degree of autocorrelation among the observation is noted. When the use of OLS and WLS or weighted least square is inefficient, we resort to the use of GLS or generalized least square in order to obtain the estimates of the parameters. The oldest use of OLS was in context of linear regression. Let me remind you, in linear regression we have a response variable y and we can have one or more explanatory variables, and the response variable depends on these explanatory variables in a linear form, and the form can be written as yi equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon, where we have p explanatory variables. The betas are called the regression coefficients corresponding to each explanatory variable, and epsilon is the error term. So, if we assume yi, y1i, 2i and pi for I equals 1 to n be a set of observations used to find a function relating the value of the dependent variable yi to the values of the independent variables x1i, x2i, xpi, then the oldest tool that was used to obtain each of these regression coefficients or the unknown parameters involved in the linear model beta 1, beta 2, beta p is the ordinary least square method. So, considering the multiple regression model with two explanatory variables x1 and x2 and dependent variable y, we have a model that can be written as yi equals beta naught plus beta 1 x1i plus beta 2 x2i plus ui for the ith observation where I equals 1 to n. Here ui is the error term, which is usually denoted by ei. The estimated OLS equation contains the parameters of interest, where the parameters are beta naught hat, beta 1 hat and beta 2 hat. This equation is written as y hat equals beta naught hat plus beta 1 hat x1 plus beta 2 hat x2. This is called the OLS equation because in this equation we have replaced the unknown parameters beta naught, beta 1, beta 2 by the OLS estimates of these parameters. We can define the ordinary least square criteria in terms of the OLS residual. By residuals, let me remind you, we mean the difference between the actual value of the response yi and the observed value yi hat. So, the residual for ith observation Ri can be written as yi minus yi hat. Now, replacing yi hat with the OLS equation, we have Ri equals yi minus beta naught hat minus beta 1 hat x1i minus beta 2 hat x2i. The idea of OLS criteria is to obtain the parameter estimates by minimizing the residual sum of squares. So, we have seen what the residuals are and what form the residuals take. So, our point is to minimize the sum of the square of these residuals and obtain the corresponding parameter estimates. So, the residual sum of square is written as sum over I yi minus beta naught hat minus beta 1 hat x1i minus beta 2 hat x2i whole square. To obtain the estimates of the parameters, we differentiate the residual sum of square with respect to each of the unknown parameters and equate them to 0. These equations are called score equations, and we obtain our parameter estimates solving these equations. Here on this slide, I have presented the derivatives of the residual sum of square with respect to the two parameters beta 1 and beta 2. We have ignored the intercept parameter, but it can be obtained in the same method, but since we are only interested in demonstrating how to obtain the residual sum of square, we have focused on the two more important coefficients of regression in this model. Now, there are some important characteristics of the ordinary least square coefficient estimators, beta 1 hat and beta 2 hat, which might be worth noting. The first of which is the estimate or the ordinary least square estimate of beta hat is always estimable if the matrix of explanatory variable or the X matrix is of full rank. If X is not of full rank, then we will need to use a generalized inverse in the expression of obtaining the beta hat. The second characteristic is that the OLS coefficient estimators beta 1 hat and beta 2 hat are functions only of the observed samples yi xi for I equals 1 to n of the observable variables y and x. They can therefore be computed for any given set of sample data. And the third characteristic is that the OLS coefficient estimator beta 1 hat and beta 2 hat are point estimators, that is, each estimator provides only a single value to estimate the unknown parameters. In general, if we have a linear model which now has n observations on a set of p explanatory variables, which can be written as y, x1, x2, xp, where y is the vector of response and x1, x2, xp are p explanatory variables, then the model can be written as y equals x beta plus epsilon. We have seen this model before, and here the OLS estimate of the parameters beta can be written in the form of matrices as x prime x whole inverse x prime y, where x prime x whole inverse x prime is called the hat matrix or denoted by H. In the next couple of slides, we will demonstrate how we can obtain the OLS estimates of the regression parameters from the canned function Lm in R, and how we can also use the OLS technique to compute the estimates using the expressions of the hat matrix, and we will see how they can be compared. Now, here is the R code to compute OLS. We have attached the data set trees which is inbuilt in R, and we write X as the matrix of explanatory variables. The two variables that we use here as explanatory variables are girth and height, and we use y as the vector of response, which here in this case is volume. We have seen that the OLS estimate of beta hat is given by the expression x prime x whole inverse x prime y. So, after we have defined our x and y's, we can now by simple mathematical function in R compute x times y as transpose of x matrix multiplication y, and we can obtain the x prime x inverse, which is given by the function solve transpose of x matrix multiplication x. So, the hat matrix in total can be written as x matrix multiplication x x I, which is the x prime x whole inverse matrix multiplication transpose of x. So, B is written as a vector which can be obtained by multiplying x x I and x y, and here we have the output that gives us the variables, which gives us the values of the two elements of the vector B, where B is beta hat or the vector of estimate of parameters. Now, on the next slide you will see how we have attached the trees data set, and here we use the Lm function to fit a regression model to the data set, where we use Lm function and regress volume over the two explanatory variables girth plus height. After we want to see the summary of this Lm function, in the R output we obtain the estimates of the corresponding regression coefficients, their standard error and the corresponding p values for the two explanatory variables that we have used. Now, we can clearly see from the R output that when we use the inbuilt R function Lm, it gives us the parameter estimates as beta 1 hat equals 5.7082 and beta 2 hat equals minus 0.4393. And the estimates that we obtained from writing the OLS formula in R had given us beta 1 hat equals 5.0440 and beta 2 hat equals negative 0.4773. And these estimates we can see that are quite close to each other. So, often we have situations where the following OLS assumptions are not satisfied. Suppose the assumptions of linear model of homoscedasticity of the error terms is violated, or the errors are correlated, which means no autocorrelation assumption does not hold, or the errors are normally distributed, this assumption is violated. Then what happens if these assumptions are not met? We know that if these assumptions are violated, our OLS estimates will not be efficient anymore, which means there could be other estimates which has lower variance than our OLS, and also the OLS standard errors will be biased. However, the OLS estimates will continue to be unbiased, which means the expected value of these estimates will be equals the actual parameter value beta, and beta hat OLS will also be consistent, which means for very large sample size it will, and beta hat OLS will also be consistent, which means for very large sample size the estimate or the OLS estimates of beta hat will approach the actual value of the parameter. Now, in cases where homoscedasticity assumption of linear regression is met, we have variance of epsilon equals sigma square I. But when the homoscedasticity assumption is violated, then we have unequal variance for the error terms, and then we can denote the variance of epsilon as sigma square sigma, where sigma is any matrix which is not necessarily diagonal, and even if it is diagonal, the diagonal elements are all unequal. The basic idea behind GLS or generalized least square is to transform our observation matrix, which is the response vector y and the explanatory variables x1, x2, xp, such that the variance of the error terms in the transformed model is sigma square I. So, generalized least square can be defined as an alternative to the ordinary least square estimator, considering what is known as the generalized least square estimator, and its form is given by beta hat subscript GLS, where GLS stands for generalized least square, equals x prime sigma inverse x whole inverse times x prime sigma inverse y. As you can see, this formula differs from that of the OLS estimate of beta hat by the term sigma inverse, which has been inserted in between the matrix of explanatory variables x. There are different perspectives from which we can understand the generalized least square estimates of beta. There are three of them that we will mention here. First of which is, it can be looked upon as a generalization of OLS or ordinary least square. In case of ordinary least square, we assume that the variance is a constant with a diagonal matrix, all the diagonal elements are equal. When this assumption is violated, we have a diagonal matrix where the diagonal elements are not equal. In this case, we can generalize the OLS to find the estimates of the parameter beta. We can also look upon GLS as weighting individuals to get efficiency. As we have mentioned before, the OLS estimates are not efficient when one or more of the assumptions of linear model is violated. We can use GLS now as a weighting individual to get efficient estimates. We can also look upon GLS as transforming the model equation to a new model whose errors are uncorrelated and variances are equal, that is homoscedastic. Now, the next couple of slides we will derive the expression of GLS that we have seen in the definition of GLS in a couple of slides ago. Suppose the linear model is given by y equals x beta plus epsilon, where variance of epsilon equals sigma square times capital sigma, and that capital sigma has eigenvalues lambda 1, lambda 2 and lambda r, where capital sigma is the matrix with unequal variances for the error terms. Now, by Cholesky decomposition, we can decompose the capital sigma matrix as S lambda times S prime, where lambda is a diagonal matrix with the diagonal elements equals lambda 1, lambda 2, lambda r, which are the non-zero eigenvalues of capital sigma, and S is any orthogonal matrix. Then sigma inverse, capital sigma inverse can be written as S inverse times lambda inverse times S prime inverse. If we decompose lambda inverse into lambda to the power negative half and lambda prime to the power negative half times S prime times inverse, we can write sigma inverse as P times P prime, where P here is a matrix given by S inverse times lambda to the power minus half. Here lambda to the power minus half is again a diagonal matrix with the diagonal elements now equals the square root of the eigenvalues of capital sigma. It is then straightforward to prove that P times capital sigma times P prime equals IR, or an identity matrix of order R. Now, multiplying both sides of the linear model y equals x beta plus epsilon by p, we have the linear model y0 equals beta 0. We now have the linear model y0 equals x0 beta plus epsilon 0, where y0 equals p times y, x0 equals p times x, and epsilon 0 equals p times epsilon. We can see that in this transformed model, we have expectation of epsilon 0 equals 0 and the variance of epsilon 0 equals sigma square times p times capital sigma times p prime, which equals sigma square times I, which satisfies the assumption of homoscedasticity. Thus, the OLS estimate of beta from this transformed linear model will be beta hat GLS equals x naught prime x naught whole inverse x naught y naught. Now, if we replace x naught and y naught by x times p and p times y, we arrive at the final result, which is beta hat GLS equals x prime sigma inverse x whole inverse x prime sigma inverse y, and the last equation is defined as the generalized least square or the GLS estimator of beta hat. Now, here are the properties of GLS that are worth looking at. The first of which is the GLS estimator is unbiased. Well, so are OLS, but under violation of linear model assumption, OLS is not as efficient as GLS. The second property is that under GLS estimation of the regression parameters, variance of beta hat GLS equals sigma square times x prime capital sigma inverse x whole inverse. Under OLS, the variance of beta hat was given by sigma square times x prime x whole inverse. But in this case, we have the variance covariance matrix sigma inverse inserted in between x prime and x. Now, if we want to look at the proof of this property, we know that beta hat GLS equals x prime capital sigma x whole inverse times x prime capital sigma inverse y, and y equals x beta plus epsilon. Now, in this expression of beta hat GLS, if we replace y by x beta plus epsilon, we will see that beta hat GLS minus beta will equals x prime sigma inverse x whole inverse x prime sigma inverse epsilon, and we know that variance of epsilon is capital sigma. So, variance of beta hat GLS minus beta will equals x prime sigma inverse x whole inverse x prime sigma inverse times variance of epsilon times capital sigma inverse x times x prime capital sigma inverse x whole inverse. And now, replacing variance of epsilon by sigma in the previous expression, we will obtain the final expression for variance of beta hat GLS minus beta equals sigma square x prime sigma inverse x whole inverse. In linear models, most commonly we use the method of ordinary least square to estimate the parameters. The basic idea of ordinary least square is to minimize the sum of square of residuals and obtain the parameter estimates. In certain circumstances, when the assumptions of linear model are violated, we then have to use a more generalized approach. Such an approach is using the generalized least square method of obtaining the estimates of the parameters. In this module, we have learned different properties, theoretical as well as practical consequences of using ordinary least square method in comparison to generalized least square method. And we will also dedicate a separate module to the comparison of these two methods using several examples from R.